let's see. Oh, the commute time and the well-being, we had a really strong R value, wasn't it? Like negative 0.98 or something like that. Would you think that the R value here is going to be what? Positive or negative? Positive. Okay, good, because you've got that upward trend. Did you look? If you just looked at this thing without seeing the R value, would you have a guess of its strength? Yeah, what would you guess? Okay. So more toward the middle of the realm between 0 and 1 rather than really high? Because, as the points are further away from a perfect line, the R value is going to drop. And that's the way it goes. But it doesn't mean that the relationship is poor. It's got to drop a lot before the relationship is poor. And I think we still have a decent R value here. What'd you guys get? 0.7? That's really good.
Is there a pretty big difference between like 0.7 and 0.8? Because like 0.7 still looks pretty blobby, but the second it gets to 0.9, it looks a lot more linear than that. So like, does
Yeah.
that up a point to a lot or so?
There's a pretty, between like a tenth of a change, you're going to see a pretty big difference in the graph. Yeah. As those points get further away. But in practice, we would even use, 0.4, 0.5 would be something to get pretty excited about. Because real life data isn't perfect. It doesn't line up and act all nice. So our R is a positive 0.70 or 0.70? Okay. What could we say that means? Means that what? There is how would we describe 0.7? It's positive. It's still, what do you think? Yeah, it's still good. It's still good. Very good would apply. Decent. And then what else? Positive, good. What else? Linear, perfect. What else? What's next? Anybody? Relationship, okay. And again, you could say correlation if you'd like. Between what? The weight and the length. Okay, bare weight and bare length. You could measure those, using survey equipment or something. You could measure those bears at a distance. I wonder how they collected this data. I guess they probably sedated them, right? No, come over here. Can you get on the scale? Okie dokie, what'd you get for the equation of the line? 1.7x.
Minus, or do you do plus?
I don't know, you tell me.
Well, it's a negative number, so I wrote minus.
Minus? Okay.
No, not negative.
No, not negative 1.7, that's positive.
Okay, and then minus 1.42? Okay, so that would be our what? Our intercept?
Oh no, it's 142.
Oh, one. Like that? Okay. Okay, so yeah, So our slope, again, there's infinitely many lines with a slope of 1.7, but the negative 142. Now, notice our x values don't start till 120, 120.5, and our y values don't start till 60. So, you know, again, that line segment is far away from the axes, but the intercept is important to lock in the actual location of that line. Does the intercept have meaning in this case? No. What would an x value of 0 mean? A bare length of 0? 0 centimeters? What does the slope mean? I'm sorry?
For every 1.6 kilograms, the total length is 60 centimeters.
Okay, how about flip that?
Oh. For every 1 centimeter, the total weight is 1.6 meters.
Perfect. The slope, or we can just say the slope means that for each additional, what was that again?
For every 1 centimeter, the weight is increased by 1.7 kilograms.
Good. For each additional centimeter of length, the weight increases by 1.7 kilograms in general. Good. Does that make sense? You guys with? How'd you do? Okay? Good. Super. Next week I'll have a worksheet for you that, in place of your quiz. So this week, no quiz of course because you have a test. So next week I'll have a class, a worksheet for you to do in class, just so you can go through this whole process and write out all the meanings as they apply to that data and blah, 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 blah. Residuals. So our next conversation is going to be about residuals. So residuals are, they describe the error, the overall error in the model, which we expect, because the data doesn't line up perfectly. Oh, you know what, I'm going to dang, I was hoping I could make my points bigger on this, but I guess not. Okay, so the residuals are, for example, this bear at 130 centimeters in length, he was observed of having a weight of, that looks like about 105. Okay, so that would be the observed Y. In other words, that's what showed up in the data. Okay, that's what we collected. But on the line, right, another bear who weighs 130 rephrase, that is 130 centimeters in length, his weight's gonna be measured at the line, right there. Okay, so if we were to, and this is ultimately what we want to do, is to take the length of a bear and estimate what that bear should weigh according to his length. So, let's say we have a bear that weighs, now, a bear whose length is, I don't know, 151 centimeters. It is estimated, his or her, I guess, his estimated weight would be y hat equals 1.7 times 151 minus 142. So we would use that general relationship to estimate what a bear should weigh if he has this length. Okay? So, you know, this thing becomes a tool. It becomes a tool. And again, that's the whole, ultimately that's the whole point. So using the line, let's see, what would that be? Can somebody run that through their calculator for me? 1.7 times 151 minus 142. So you're okay with that, right? You're just plugging in a length value? Does that make sense? You guys with me? Okay. Someone have a calculator handy? 114.7? So that bear should weigh about 114 kilograms. 114, 115 kilograms. Make sense? Okay? Now note, we can't use this model or this tool for bears under, say, 120 centimeters in length, or bears over, what is that one, about 170? 165, 168, whatever it is, or above that length. Because all we know is what we have data from or for. So if we were to, again, if we would get another bear, so once this data is collected, then these bears are back off in the wilderness and we're done with them. And we simply wanted that data to be able to create this tool. So if we were to have a bear that is 130 centimeters in length, his weight would get estimated using the line. So it would be right there. Does that make sense to everybody? But his actual weight, the weight of the bear that we observed, was way up here at about 105 kilograms. So that vertical distance is called a residual. And again, residuals are the vertical errors in the model. So every one of these vertical distances between a data value and the line is a residual. Oh, I knew there was another data value down here somewhere. There it is.
There's one on the far bottom left, too.
Oh, this guy?
Yeah.
Yeah, I drew that little tiny line there. It's really close to the line, so residual is small. Again, we expect error. And we can find, so at each one of these data values, unless the line goes directly through that ordered pair, that data value, we're gonna get some kind of residual or some kind of vertical error. If you need to find a specific residual, they're calculated. So this is the observed y, and this would be the predicted y. So each residual is the observed minus the predicted, observed y, minus the predicted y. And that's how they're calculated. Some of them are going to be positive, some of them are going to be negative, because some are below the line and some are above the line. Here, you've got your observed is larger than your predicted, so that's going to be a positive residual value. If you're asked to calculate a residual, you would take that y value from the data. You would take that y value by plugging that x into the regression line. But the easier way to do it is just have a StackCrunch generated. So it can generate all the residuals for you. If you go back to the regression, what do I want to say, tool, see where it says there's a box down in that I don't know, that command. It says save, and see where it says residuals? So if you save the residuals and go compute, okay, I'm gonna get rid of my scatter plot there. So there is the calculation of each residual depending on the ordered pair. So again, each residual corresponds to an ordered pair or an observed data value. So at each data value, it calculated and is storing the residuals. It's if you go back to that. Oh yeah, so you're going to bring up your regression. And then scroll down and see where it says save. Click residuals. Yeah. And it'll generate them for you. So individual residuals are easy to find that way. Then on your, what you're going to want, a value that you're going to want, is the sum of the squared residuals. So the sum of the residuals squared is given by, I can't remember if it's, It's this value right here at the bottom of your output where it has, it says analysis of variance table. Don't worry about any of that, but where it says error and SS above it, that's your sum of your squared residuals. So it's 4350.4. So before we talk briefly about or maybe I started to talk about how do we know, why do we know to use this line? Why this line? Why could it not be a slightly different line? Why this line? The formulas that generate the slope and the y-intercept automatically minimize that calculation, the sum of the squared residuals, because we want our overall error to be as small as possible. That's the goal. And the formulas that, again, are used to generate the slope and intercept automatically do that for us. And that's why they call it the least squares regression line, because it minimizes the squared residuals. Why do they square them? To make them all positive. Because some are below the line, some are above the line. And if you were to just take all of these distances and add them up, they'd be 0. The positive distances and the negatives would cancel each other out. So we square them to make them more like distance. I would think absolute value would be better because, but I don't know. I didn't make this up. But anyway, they automatically minimize that error. So yay. Let's see what else is in. So we're kind of 4.1, 4.2 today. So any other line whatsoever is going to make that number bigger.